Hello everyone, and welcome back to another little video where I'm going to be showing you how to work with polar coordinates in Calculus 2. Specifically in this video, I'm going to be showing you how to convert between polar coordinates and their Cartesian equivalents. To do that right now, I've laid out a grid, a Cartesian grid over here. I've thrown on it a particular point P with no specific coordinates. And what I'm going to do is, I'm going to give this P here a vector that connects it to the origin. This is nothing else than your R component right now in polar coordinates. That's what it does. It literally rotates around over here to any point it has to go here, and it basically connects the origin to that point. But we can't, of course, specify the position of this point P without giving some other information, because there's, for example, other points that have the same R. In fact, any point right now that is part of this circle here with radius R that I'm trying to fit in, any point that is part of this circle, of the white circle, is actually having the same R coordinate right now. So we need to distinguish what makes this P unique by providing some other information, namely an angle. And what angle can we provide it with? Well, again, we've chosen to use the x-axis and specifically the positive x-axis as a reference for that angle. So again, this angle would be this theta if you're in math, or phi if you're in physics. That's what we call it. And it puts us, again, it gives us the angle between our red vector R and our positive x-axis right here. So now we've uniquely defined the position of point P. From here, what we can do next is we might want again to convert back into Cartesian coordinates. So to do that, we can break down the components of this R vector right now into their respective y and x, as you can see here. And to get right now y and x, we notice that we have a right angle geometry every single time here. And our y component is nothing more than r sine theta right now, versus our x component is nothing more than r cos theta. And really, those are the two equations you need to be equipped if you're going from polars to Cartesians. We will combine these two equations in a meaningful way in the next video to go from Cartesians to polars, and we'll derive some more equations that we need. But for now, this is sufficient. So again, I'm going to go down to the examples that I have for you laid out right here. So I have 3 points that we want to convert again from their polar representation to their Cartesian representation right now. One thing I want you to do every single time you encounter these kinds of problems is to draw a grid. Draw a unit circle grid specifically, where you're going to try and interpret as much information as possible from those points that you're given onto that grid. And it will make your life so much easier when trying to make conclusions about what you need to do. And it will allow you to even take shortcuts, as you will see in one of these parts over here. So to start off, let's see this point over here. We are given the size of the vector that you saw earlier. So we're given the fact that it's 1 in length. And we're given right now that it makes an angle pi over 4 with respect to that x-axis. So again, we can come in and put that information. There's the 1, and there's the pi over 4. So if I'm wondering to find again what the x and y components are right now, they're really easy to obtain. Simply here for the y component, take the 1 and multiply it with the sine of pi over 4. And for the x component, take that 1 and multiply it with the cosine of pi over 4. Now pi over 4 is a special triangle. Maybe you remember it, maybe not. It's the 45-45. And we know that the sides against each 45-degree angle are 1s, and the hypotenuse here is root 2. So if we're being asked about the sine and cosine of pi over 4, notice that they're exactly the same. 1 over root 2 and 1 over root 2. So we can get our y component right now as 1 over root 2, and our x component is actually going to be exactly the same. Both of the y and x are positive. We can see it right now from the position that that point, again, the point of interest is at. It's at the first quadrant, but the x component again over here, but also the y component over here are both on the positive x and y axis respectively. So I can conclude here that my point of interest is at 1 over root 2 and 1 over root 2 for its x and y representation. And that's it. So we can do the other one, the other example over here. Let's see what we get from that. We are told the size again of the r vector, it is 2, but we're given the angle as a negative representation. So what's up with that? Well, in polar coordinates, positive angle is measured again over here counterclockwise, this direction, and negative angle would be exactly the opposite. So if I'm below the x-axis here, there's two ways we can measure that angle. There's this way, which is a positive angle right now, and there is this way, which is a negative angle right now. So if we're being given negative pi over 3, or negative 60 degrees if you must, that means we must be, again, we take our vector and move it 60 degrees below the x-axis instead of above. And I've got pretty much what I need. As you can see again, I've got the 2 here. I know that this is pi over 3. And the components, I can see them very clearly for the y and x right now. How do I get the y? How do I get the x? Same procedure. For the y, we can only get the size of it. We'll have to think about the polarity once we're done. So the y component is going to be the r size times sine of pi over 3. And the x component is going to be the r size times the cosine of pi over 3. Now pi over 3, again, part of a special triangle, the 30, 60, 90. Against the 30 is 1, against the 60 is root 3, and the hypotenuse is 2. So this guy here is 60 right now. Cos of 60 is 1 over 2, as you can see. And sine of 60 is root 3 over 2, as you can see over here. All right. So again over here, we can simplify these a little bit. 2 times 1/2 is just 1. 2 times root 3 over 2 is just root 3. So we would conclude that the point, for example, over here would be 1 and root 3, right? Not so fast. Because again, one of these components is negative. We can see here that our point of interest has a negative y component, while the x is positive. So whatever we got for the size of y right now, we have to make sure we put in the proper sign. So that's where the diagram again shines to show you that. You can't do these questions without a diagram. So this is the correct representation again in Cartesian coordinates. All right, so far so good. Let's see the last one over here, which is interesting. It says 3 and pi. So again, to think about this, I would take my r vector of size 3 right now and rotate it pi radians, so 180 degrees on this direction right there. So knowing again that the size of the r vector here is 3, immediately allows me to tell what the coordinates of that point are going to be. This is there has to be no other choice here besides negative 3 for the x right now, because we're on the negative x-axis, and 0 for the y, because again, we're exactly at 0 on the y-axis. So in fact, for this point right here, I don't even have to use any equations. I can read it straight off the actual plot, and I'm just showing you once again how powerful it is to draw the situation out in these kinds of questions. So immediately we got what we needed over here. So those are the 3 examples I'm going to let you again see as a beginning again for converting between polars and Cartesians. In the next video, I'm going to do the opposite. So I hope you found the conversion here from polars to Cartesians helpful. If so, consider subscribing.